might start the proceedings because we have the attendance. Good morning, everybody. My name is Vijay Kumar. I will be co-chairing with Gordon Chan for this session. This is a combined session between the Radiopharmaceutical Society and Australia-New Zealand Society of Nuclear Medicine, RPSC. It's a combined session. We have very interesting, internationally renowned speakers, and we are privileged to have them all here. The next speaker is Joseph Lipolo. He's going to speak about F18 labeled aluminum fluoride, labeled radiopharmaceuticals, preparation and evaluation in vitro and in vivo. Joseph Lipolo is from the Rapid Laboratories, Medical Technology and Physics, Sir Charles Gardner, WA, in Australia, Western Australia. Joseph.
Thank you very much. How do I click? There we go. So yeah, today, can I just say ahead of time, it's a really great thing to speak to this group of people today. I will speak to you briefly about some aluminium fluoride labeling projects I've been working on. I'll begin around talking about aluminium fluoride ubiquicidin, just as a test compound, the lessons learnt from that translated across to labeling PSMA HBED, and some valuation of that compound against what I'll call the gallium gold standard in PET and in a mouse model. So firstly, aqueous fluoride labeling, in case you haven't heard about it, is one of those ways of getting around the traditional problem of traditional carbon fluoride bond formation. It's typically very water sensitive traditionally, and you need to spend a fair bit of time drying down that fluoride before you can use it, traditionally. Instead, you can form a hydrolytically stable bond between fluoride and some other candidate atoms, such as boron, silicon, and aluminium. The champion of boron is in the room at the moment, so I'll be a bit careful about what I say. But the aluminium fluoride method is very similar to the gallium chelation. If you can chelate gallium to something interesting, there's a good chance you can chelate aluminium fluoride to it as well. It happens at the same pH and often with the same macrocycle, in this case, NOTA. So the test molecule I looked at was ubiquicidin. A method for making this is a multi-step procedure involving first making a prosthetic group, SFB, and adding it to the lysine residue of ubiquicidin, which is the 29 to 41 sequence, and that takes 150 minutes. However, you can commercially buy the NOTA version of this to chelate gallium. So I thought, well, if I can chelate gallium, why not try aluminium fluoride? And it's a subject of a previous talk, but you can do that. I have done it in a much shorter amount of time. But the lessons to be taken from this are, first, you need to take a very large amount of fluorine activity and put it in a very small volume. Typically, gallium reactions are about 5 mils. You need to get this down to much, much less than 1 mil. The second challenge is a very high precursor concentration. I've optimized this around 85 micromolar, about 50 micrograms per synthesis. Gallium, again, is much, much less. And the third thing is it's not fully aqueous. It's not 100% aqueous. There is water in there. But you need 50 to 60% of ethanol, and much more than that, and you'll denature your peptide. That all taken together, 20% yield in 20 minutes. The difference between 20 minutes and 150 minutes is a loss of more than half of your yield just from decay alone. But the question is it stable? Will it hold together in plasma? And the answer is it does, it does fall apart very quickly. So if you can see here the top trace, that is 100% bound activity with no free fluoride, but from 30 minutes on, you can see that there is a small but rapidly increasing peak for free fluorides, and the peaks for bound peptide go down. And if you plot that over time, you just look at that, those blue squares, we're reaching about 50% purity in only 1 hour. But interestingly, if you take the gallium compound, which is reported to be stable, under the same stability protocol, I'm actually observing an increased stability of aluminium fluoride. So this remains to be properly elucidated. Perhaps this stability test is too harsh, but the same protocol using some test compounds, dotatate, technetium bone scan, FDG, and even gallium PSMA showed no negligible degradation after 4 hours. So perhaps it is more stable than the gallium. But it kind of begs the question, doesn't it? If I can label a compound designed to label gallium, why not go ahead and label it with aluminium fluoride and take advantage of all those benefits, better physical characteristics of fluoride? You can make many more doses with fluoride than you can with gallium, and that's the challenge for radiochemists today. These are the key papers for aluminium fluoride. If you take all those together, general reaction conditions are just what I said previously. You need a very small volume with a very high concentration of PSMA. You get a very wildly varying amount of reported yields depending on whether it's manual or automated or some other factors, but I'm getting basically essentially something similar, more than enough to do a few cell tests, a few mice. But the question is it stable? Will it hold together? And the answer is no, not in my hands anyway. After 1 minute, it is 100% bound, but from 30 minutes on, that peak for that bound peptide goes down. We don't get a traditional free fluoride at the injection volume. It's actually in the background. That's to do with a problem with C18 HPLC. It's an interesting question to ask me later, and I can go into it. But if you plot the amount of bound to unbound activity over time, again, it drops off quite quickly, about 50% in half an hour, compared to gallium PSMA, where there was no degradation observed in this same plasma stability test. Published results, again, do vary, but generally they say greater than 90% in human plasma for at least an hour. More interestingly, if you look at the finer details, they all talk about instability in formulation, unstable even in saline. But it's okay if you add 1% ethanol. But 1% ethanol is bad if instead you use acetate buffer or PBS. But phosphate buffer is okay on its own. So there's a bit of variation here. I don't want to cast aspersions on all this work because some of it's all very, very good. I'm just saying, in my hands, it's not that stable, and it does give you a bit of pause for thought. There have been some animal studies done. They're not all in the same animal models, and to date, I don't think there has been a head-to-head study with gallium PSMA with the same cancer model in the same mouse. So that's what we looked at doing. So that's the gallium compound that we're trying to replace. This is the aluminium fluoride compound, and this is PSMA 1007, which is now a commercially available compound which I've developed at Sir Charles Gardner as well, topic of another talk. But if you inject this compound as soon as possible after endosynthesis, we do in fact hit the target. That's a 22RV1 PSMA positive tumor there on its left-hand side. Very high uptake in the kidneys and bladder for urine excretion. And I hear a few bit of laughter. That's not a PET-CT fusion image. That's actually bone uptake. So you see quite a bit of bone uptake in the spine, in the joints of the mouse, and that's going to be an issue if you're looking for any metastasis, any kind of cancer in the bone. That's a big issue. If you compare it against gallium PSMA and PSMA 1007, again, all of them you hit the target. So there's the tumor there. There's the tumor there underneath the kidney there. And there's the tumor there for PSMA 1007. If you compare it to the blocked images, these would have been blocked with ZJ43. You can see all of that uptake is blocked and all of that activity is shuttled to the bladder in all these cases. So you can see that uptake is all PSMA mediated, that's confirmed. But that bone uptake does not go away. So that's just confirming very rapid in vivo instability of free fluoride. Technically aluminium fluoride, but that goes to the bone as well. And interesting as well, because of the increased resolution of F18 compared to gallium-68, you can actually see the spleen here, which you can only barely see in the gallium, but it's all very interesting work and would be quantifying that over time, ex vivo as well, but I don't really have time to go into that. So my conclusions are aluminium fluoride labeling has been successful, but it depends very much on the choice of chelate, and I think we need very, very careful quantitation of fluoride impurities. Ubiquitidine was perhaps more stable with aluminium fluoride than gallium, but aluminium fluoride PSMA was in fact unstable in plasma, and though in vivo successfully reached the target and was on mechanism, there was significant bone uptake, which I will argue is going to preclude any use clinically. But indeed, there is excellent uptake in excretion and stability for PSMA 1007 in exactly the same in vivo model. So with that, I need to thank a lot of people. So this is basically all of Perth. I'd like to thank my group, my supervisors who have allowed this kind of work to continue in the spare time. Also, I'd like to thank Rick, who's helped me process the images, Kirsty, who did all the animal work, and Brenton, who acquired the images. And all of this was done in Perth, in the States' only small animal imaging facility for PET. I commend it to you greatly. Thank you for your attention.
Thank you, Joseph. That's a very interesting talk. I was just wondering, most people use DOTA or NOTA or NODAGA, and you have selected NODA for F18. Is that a better specific chelator for F18 or?
Yeah, so the main group working with aluminium fluoride labeling, the group that was able to get the first clinically used compound labeled that way, alphatide, tested all chelates around. They found NOTA was the best. You'll notice that one binding site in aluminium has been taken up by fluoride. So the argument is if you have a pentadentate ligand rather than a hexadentate ligand, that should give you better stability. And the fact that it was commercially available, already attached to ubiquitin, was a big compelling factor for me to try that out, yeah.
Great. Any other questions from the floor? I can take one more. Yes? Come to the microphone, please. Or speak loud.
Thanks for the talk. It was awesome to hear. You use aluminium fluoride as your something that chelates your ubiquitin. Have you ever considered gallium fluoride, and why aluminium fluoride and gallium, but not gallium fluoride, cold gallium and hot fluoride?
You got me there. It's the easy answer is it's what's been done in the literature. I'm not sure exactly if that's possible. I think certainly the aluminium fluoride bond is one of the strongest there is. There's no real dispute that aluminium is going to disassociate from fluoride in vivo. It's more a loss of aluminium fluoride unit. Gallium fluoride, I used to be an actual chemist, but I'm not anymore. I'm sorry, I'll have to follow that up with you later.
When you elute the gallium generator, you only get gallium chloride, and for you to make gallium fluoride is a challenge. So that's one of the reasons why people don't use that.
I think, do you mean cold gallium, right?
Yeah, like one approach could be you could have the cold gallium chelated to your molecule. Cut the fluoride substitution group, cut it, kick off another group. Instead of making gallium fluoride at the beginning.
Yeah. So hypothetically, if we could do that, we'd still have an issue of, well, you have to establish the stability of the complex as a whole, which again is probably worth looking into, yeah.
Okay, we'll have to move on to the next speaker in the interest in time.
Thank you, Joseph.
So the next speaker, actually, Joseph's paper and also the next three papers are all entrants in the Shimadzu Award, which is a award sponsored by Shimadzu for $2,000 for the best paper. The next speaker is Associate Professor Uwe Ackermann, who has affiliations with a lot of different things here. Tumour Targeting Laboratory of the Living Newton-John Cancer Centre, School of Cancer Medicine at La Trobe Uni, Molecular Imaging and Therapy at Austin Hospital, as well as the Department of Medicine at the University of Melbourne. And that helps explain why I can never find him. But
right, well, thanks, Gordon. It's a wonderful...
His talk will be harnessing analogues of the oncosin-1 for radiotracer imaging of targeted therapy resistance.
I think, Gordon, your introduction is taking longer than my talk, but anyway. Today I'm going to talk to you about work not that I've actually done, but work that was done by one of my PhD students, and I hope my presentation is going to do him his work justice. So the KRAS mutation we thought would be a valuable biomarker because it is part of a normal sort of growth signaling cascade. There are activating mutations that can occur that result in abnormal signaling, and there's about 30% of cancers, including pancreatic, colon, and lung cancers, that exhibit that. And it confers resistance to some form of treatment, especially antibody treatments against EGFR. So one of the compounds that was sort of identified in a screen was Concurrent. And there have been sort of, I suppose, more structure-activity relationships done on this, but the Concurrent certainly has shown to be, supposedly selective for the KRAS mutations, but still the mechanism of actions is not very well understood. So our aims was basically to investigate the biological properties of Concurrent analogs and the derivatives, and develop F-18 labeled versions of it, as well as evaluate their potential for PET imaging. The proposed targets that we had basically were these compounds here. Pretty much 6 of them were, aldehydes, aromatic aldehydes. And then there was one hydroxy compound that, actually we wanted to make 3 hydroxy compounds, but unfortunately only one of them has actually worked. So these were our targets. And of course, oops, I'm not sure why this is black now. Yeah, okay. So the synthesis of the cold standards is fairly easy. You do a fairly standard. Okay, there's some cursor moving on my screen. But anyway, so you do a fairly standard sort of formulation of this precursor here. I'm not so sure whether I can use the pointer, but anyway. You react this with the appropriate aromatic benzyl bromide, and you get your cold standard compound that you can reduce with sodium borohydride to form the alcohol as well. So we then, of course, went on to try and develop the radiochemistry, and as Giancarlo has pointed out, these aromatic fluorination reactions with F-18 are fairly limited. We have the obvious restriction of a relatively short half-life of F-18, but also the problem that really there is very few sort of reactions that are suitable when you don't have an activated aromatic ring. So as Giancarlo again pointed out, the hypervalent iodine compounds, the iodonium salts, were probably sort of the first things that we thought of. And you can make these on paper, at least. It looks like fairly easy, but the biggest problem that we had was actually the instability of our aldehyde using the oxidative conditions that you actually need to generate them. So these compounds, unfortunately, in our hands, were not very stable, even though you can make the corresponding iodo compound very easily. But then when you try and, as I said, generate the iodonium compound from it, you actually do observe a lot of decomposition. Even some of our model compounds have not really resulted in anything that was even remotely stable, let alone label in our hands. So the summary of the iodonium salt certainly for us was that it was totally incompatible with the one-step labeling approach. The precursors, as we said, have got issues with reproducibility and stability, and also the harsh reaction conditions for the actual precursor synthesis made it pretty much impossible for us to generate any of them. Again, what Giancarlo has pointed out, a lot of things are now being done sort of more recently with boronic acids and esters as well, and that's kind of the synthetic route to these compounds. So you make the esters first, basically, and then you hydrolyze them to form the acids. But because of the ease of the synthetic accessibility to the esters, we investigated the radio labeling of esters first. So, as I said, it is fairly easy. These are relatively standard conditions on how to make them. We were fortunate, of course, that we could use the aromatic iodo compounds that we used when we tried to make our iodonium salts, and the yields are really, really good. But there is also the possibility, of course, of doing a sort of two-step reaction as well, where you basically generate from a commercially available boronic ester, you can generate your precursors. So both, pathways are, pretty much give you the same yields. The radio labeling, now this is really a tricky part. For those of you who have actually worked with these things, it is really extremely difficult to find an eluent system in the first place that actually works for you as well as reaction conditions. So, I mean, when you look at this list, really, you can see that a special triflate eluent was what we really needed to have. A copper triflate pyridine, copper 2 triflate with a certain amount of pyridine. That was really the only system that worked for us, with about even 4.5 mgs of cryptofix, and there was always a slight sort of presence of oxygen that we seem to need to actually really promote this reaction. So again, but once you've worked out what your reaction conditions are, it is reproducible, but there's so many factors, as you can see. It really took this student a long time to find out the best labeling conditions. So again, when you look at the results, you can label this in the ortho, meta, and para position. Yields are just over 10%. When you look at, for example, the UV trace and the radiation trace of this ChemO2, which I think is the meta compound, you can see how the results actually are true. So we then went on, when we had the cold compounds in hand, to determine our IC50 values using colon cancer cell lines. And the ones that we decided to use were the Colo 205 and SW480 and the LIM 215 as a control. So the LIM 215 is an EGFR positive cetuximab sensitive cell line. Colo 205 has got a BRAF mutation which sort of sits above the KRAS mutation. Is not cetuximab sensitive, and the SW480 is the one that has the KRAS mutation and is also not cetuximab sensitive. Now, what we were hoping to see, of course, was that we could differentiate with our compounds between BRAF and KRAS. And when you look at oncrasin 1, that certainly is slightly the case. I mean, the IC50 for the Colo 205 is 12.33 and 2.75 for the SW480. But when you look at ChemO1 and ChemO2, you can see that there is, not really a significant difference between Colo 205 and SW480. So at this stage, we thought, well, we probably, have given this project out a little bit too early, because clearly the F19 compounds seem to sort of take that selectivity away for our KRAS mutation. And we then sort of thought, well, when we then looked at the literature, we sort of realized that there was also another interaction for these compounds, which is a SALT1A1 interaction. And SALT1A1 is a sulfotransferase that is involved in estrogen regulation. But most importantly, it is really an essential enzyme to actually use for tamoxifen to actually work as a chemotherapy. So tamoxifen is actually a product in itself, so it does need an oxidative metabolism to be converted into a hydroxy compound, and then SALT1A1 basically sulfonates the tamoxifen. So we thought, well, maybe we can use this compound as an indicator of treatment resistance or response to tamoxifen. And again, there is, obviously this is a breast cancer project, so it's moved a little bit from colon cancer to breast cancer. But the two cell lines that we used were MCF7 and MDA-MB231. So MCF7 have got SALT1A1, and the 231s are SALT1A1 negative. The biological evaluation was relatively good, actually. So we did get some response here for the IC50 for the compounds in the estrogen-sensitive MCF7 cell lines, and the IC50s were a lot higher, obviously, in the MDA-MB231 cells. So we then had a look at the radiotracers and, try to see whether they get metabolized in vitro at least. So we have a little S9 liver fraction assay that we use, where we look at the metabolism over 2 hours, and you can see that there is no metabolism. The preclinical evaluation in sensitive cells, we did the PETA-MAR studies, small animal PETA-MAR studies with MCF7 tumors. And when you look at the time activity curves, you can see that there is a slow clearance from muscle, but the tumor tumor levels sort of stay elevated, and the tumor, of course, is indicated by the actual arrows. The insensitive cell lines, there's pretty much no significant clearance from tumor or muscle. But when you look at the tumor to muscle ratios, you can clearly see that, I should have probably shown this here, that it actually goes up in the sensitive cell lines over time. So in conclusion, there's of course a lot of work to do, or still to do, but we synthesized 7 cold standards. We established the methods of radiolabeling using the Boronic esters. We evaluated the toxicity in colon and breast cancer cell lines and found obviously that it really is a better marker in breast cancer than what it is in colon cancer. And we did some preclinical evaluations in terms of metabolism and in vivo imaging as well. And of course, thanks to all the people that were involved, especially Alexander MacDonald, who was the PhD student that did all the work, and he certainly did, I think, a wonderful job going, from something that we probably have given out a little bit too early, and very, very difficult radiochemistry, of course, as well, to making this project a success. And thanks for your attention.
Okay, time for one quick question. Is there any questions from the floor?
Yep.
Just a comment on the radiolabeling with the boron copper chemistry. We did a lot because we have this license for that patent as ABX, and it seems to be very crucial to use dimethyl amide as a solvent. The conversion goes up very dramatically. We don't know, but that's known from metal organic chemistry. Sometimes it has an effect. And also switching carbonate to oxalate. So we use always 4 milligram potassium oxalate. It gives you right away 50% conversion. We never brought it to 70 or 80, but at least it's better than you have 10% or what we normally see with DMF and potassium carbonate. So
yeah, I mean,
and that example should actually label quite well, I think, with these conditions. So.
Yeah, it's certainly something to try. I mean, we didn't know. I mean, there's just so many options, and it's still a very new field, I suppose. So it's
definitely.
There's a lot of things that you can explore still. Yeah. But I mean, as I said, even in our hands, we never really sort of gotten beyond 20%.
No, we saw the same. Then just switching to DMAA, it's 50%, and you have no explanation. It's just trial and error. So
Thank you very much. Thank you, Yubi.
Okay, so the last paper in this session and the last of the 4 entrants in the Shimadzu Award is from Uwe again. Uwe's come up for more things, and he's going to speak on the development of mTOR C1 specific antigens for the evaluation of HER2 targeted therapy using PET. So,
okay, well, thanks, Gordon.
Okay.
It was a bit of a shorter introduction, but again, this is a project that not I have been working on, but one of my PhD students. mTOR is another one of these regulators of nutrients and energies, and is sort of downstream from all the growth factor receptors, and especially the overexpression of HER2 has been linked to activation of mTOR and subsequent poor prognosis, and in particular the constitutive mTOR signaling in breast cancer has been correlated to Herceptin resistance in a wide range of studies. Again, we thought imaging of mTOR might be, a good thing to be able to do, and we thought we can base our PET agent on a structure that was published a little while ago, Cambridge 5219657, high throughput screening by people at Harvard. And again, just like with the previous projects, there have also been extensive structure-activity relationships done by especially Salome and others. And so out of these many compounds that they have actually screened, we picked one that we thought might be particularly interesting. We thought as a reference compound we use one that is already known, which was done by Salome et al. But then the proposed radiotracer, we thought rather than having a piperidine sitting on top of the other piperidine, we thought we'll put a piperazine in there and do some click chemistry by attaching a propargyl group. So we call these class 1 inhibitors, and they bind to mTOR complex 1. So in order to make the benzopyrene backbone, again, fairly standard bromination of this dihydroxybenzene gives us the bromo compound. Now, we did manage with palladium acetate and a vinyl benzene to make the intermediate here. I should actually figure out how to use the pointer, but anyway, let's try this. Yeah. And unfortunately, the subsequent ring closure did not work for us, so we did explore a second route, which actually is sort of, that generates all the compounds in situ, so with acetyl chloride and the various palladium catalyst and 5% copper as well. We made this compound here, which then, by adding potassium hydroxide to the whole crude reaction mixture, so you don't work anything up here, you don't isolate anything, you actually do close the ring, and you get your target compound in about 83% yield. Again, a fairly standard ortho formulation worked pretty well for us. But then the subsequent reductive amination with sodium cyanoborohydride and acetic acid did not give us the desired compound. So we had to change our strategy and introduce the methyl group first. And then the subsequent reaction steps actually worked. So you can see with the metal compound, with the model compound that only has a piperidine in there, it works quite well, 54%. For the reference compound, it works quite well as well, and of course also for our radiolabeling precursor too. So the cold standards we could synthesize quite easily then by reacting fluoroethyl tosylate with sodium azide to make an intermediate fluoroethyl azide. Again, you don't isolate this, it's explosive, and so you don't necessarily want to distill that off or anything like that. And then a fairly standard, click chemistry reaction gives you your cold standard. And for the radiolabeling, we followed pretty much the same path. Tosylethyl azide with F18 gives you fluoroethyl azide. You can distill this across into a separate reactor vial. We automate this with our FlexLab modules. And so you distill this into the second reactor where you do your click chemistry, and you get in about 40% radiochemical yield. You get your radiolabeled compounds. And again, just to show you the HPLC traces of the cold and of the hot compounds. So for the radiochemistry and cold chemistry, we certainly managed to get our radiolabeled compound done in 40% yield. We can make up to 146 millicuries, which is quite good. Radiochemical purity, specific activity is all sort of within the range that you expect from F18 compounds. And in our Essner liver fraction assay, we could also demonstrate that it was metabolically stable. Now, of course, the question then was, can we differentiate between breast cancer cells that are sensitive to mTOR inhibitor treatment and cells that are resistant, and do some micro-PETMR studies to really observe the uptake pattern. When you look at the list of breast cancer cell lines, we identified everolimus sensitive ones as BT474 and HCC1419, and the resistant ones are the 231s and the 468s. They're actually quite fairly standard breast cancer cell lines. So the uptake then of our radiotracer in those cell lines, you can see they are a bit higher in the sensitive ones than in the resistant ones, and we then moved on to do some PET murine xenografts, and again, these are just our MR surface rendered models. You can see the tumors quite well with the surface rendering. We have various mice here, and when we look at the actual location of the tumors, again, it is fairly obvious. When you then bring in the PET, to sort of co-register them and do the time activity curves, you can see that for the 474s, you know, the activity in your tumor goes up from the muscle that clears, and in the 231s, the tumor, again, sort of, there's a bit of inconsistency, I guess, in a way, but tumor and muscle stay relatively stable. And when you plot this over time, you can see that the radiation ones, sensitive ones, show a slightly increasing tumor to muscle ratio over time than the resistant ones. So again, you know, as a response marker, we have an average tumor to muscle ratio of 1.7 in positive and 0.9 in negative mice. And we think that the tumor to muscle ratio could certainly be used as a marker for patients that are responsive or resistant to mTOR inhibitor treatment. So just as a summary slide, of course, we synthesized and radio-labeled the class M1, class 1 mTOR inhibitors. The internalization assays showed increased uptake of the compound in red OVO1 sensitive cells. And the PET imaging, again, also showed the contrast between the sensitive and resistant cells. And the compound could be a potential marker for patients that would benefit from treatment directed against mTOR. And again, you know, acknowledging, it's actually me, that it should be Christian Wichmann. Now, there he is. Yeah, thank you for your attention.
So, is there any questions for Uwe?
Everyone is hungry, Gordon.
Yeah, okay, well, that is, yes, that is the last paper for the lunch, and that concludes our session. So, good luck to all the Shemadzor Award entrants. Lunch is available on the ground floor, and it says there to sign the wall of friendship. I didn't know there was one. Now, for the members of the ANZ-SNM, room 219 is the AGM at the moment. If you want to go to the AGM, you can go straight across there. All right, thank you.